So I feel like I have to maybe apologize in advance because I have not had as much time as I would like to prepare or practice these lectures, even in the shower. Last night I had one of those nights where you just can't really sleep, and then at 2 in the morning you decide to take a sleeping pill. And then, so I'm pretty sure that I'm actually here, that this isn't a dream. Anyway, I like to think that I'm here among friends, so if this is not quite as polished as it ought to be, please forgive me. The other thing I need from you, though, so this is a wildly interdisciplinary audience, right? We have people here from fields that normally would never speak to each other, like applied mathematics and pure mathematics, for instance. So, with a few outliers like theoretical computer scientists, also known as mathematicians being paid an engineer's salary, I'm a physicist by training. So things like the notation for, the transpose and the inner product and things like that, just stop me if you're not sure what I'm saying, okay? So I want to start by something which is not related to machine learning, and because then I'll go into things closer related to machine learning, or I should probably say Bayesian inference, in a roundabout way. So I want to start by picking up on what Josh was saying at the end of his lecture last time, but I hope this will be also intelligible to people who weren't at that lecture. So there's a particular tensor that a number of us are interested in. Josh said that you either love it or you hate it, but I'm pretty sure everyone who hates it because they loved it for several years and were unable to figure anything out about it. So it is this tensor, and partly because I was trained as a physicist, I like to write some of my indices on the top and some on the bottom. This is popular in general relativity, for instance. So, but think of these as, if you wish, think of this as an n cubed by n cubed matrix, where these three things, each of which run from 1 to n, index the rows, and these three things index the columns. And here is the particular tensor that I'm referring to. And what this is, these things are Kronecker delta functions, or really they're identity matrices. Each one of these is 1 if these two indices are the same, and 0 otherwise. And note this is ij prime, jk prime, ki prime, so there's a funny cyclic thing going on here. And in fact, the way I like to write this matrix is like this. This is how I like to represent this tensor. Because each of these things just connects, the meaning of a wire here is a demand that one index be equal to another. What does this have to do with matrix multiplication? Well, now apply this, let's see. I mean, the fun thing about tensors, right, is that we have all these different ways to contract them with each other or with themselves, and only a few of these really seem like matrix multiplication. But, sometimes we have to stand on our heads to call it matrix multiplication. So I want to apply this, viewed as an n cubed by n cubed matrix, to the tensor product of three n-dimensional matrices, n by n by n, and what I mean is I'm going to put, I'm going to have a, let's see, well, let me do it this way, I prime I, and B j prime j, and C k prime k, and I've lettered these because I want this to be equal to that, this to be equal to that, and this to be equal to that, as I would do with matrix multiplication. But then I also want this to be equal to that, and this to be equal to that, and this to be equal to that. So really I'm taking the trace of this, And diagrammatically, that takes A, B, C, and then the trace, of course, just does this. Because in this diagrammatic world, the trace of a matrix M just connects it to a loop, which takes its, if you will, incoming row and sets that equal to its outgoing column. So this is the trace. Are a lot of you familiar with this sort of diagrammatic thing? I'm very fond of this. So for instance, we sometimes when we're teaching our students about the tensor product, we pose to them as an exercise that A tensor B times matrix times C tensor D equals AC tensor BD, right? We pose that, we ask them to show this. But this is a tautology because both of these are simply, here's A tensor B, it's these two things next to each other. And here's C tensor D, and there it is, right? So both of these expressions are this one diagram. So it's a proof, if you will, by picture. Anyway, when I take this lovely little cyclic gadget and attach it to A, B, and C, which means multiplying it by A tensor B tensor C, and then I take the trace, which means looping everything back up to the top, what do I get? Well, I get A, B, C back to A, so this equals the trace of the matrix product ABC. Okay. So the matrix multiplication tensor is just this. It's just this odd, cyclically shifted, almost identity matrix, right? I mean, if this was I prime, J prime, KK prime, this would just be the n cubed dimensional identity matrix, or if you wish, the tensor product of three n dimensional identity matrices. All we have to do is figure out how to get it to slide over. But, so as Josh was saying, what do we want to do if we want to compute the matrix product efficiently? And by the way, you might think that computing the trace of the product of three matrices is sort of a different task than computing the matrix product of two matrices. But actually it isn't, because if C was a matrix of variables, then this would equal, another way to write this would be the inner product of AB with some, that's what I mean, that means the transpose. And so if I had a bunch of variables here, those variables would simply pick out all of the entries of AB. So computing the trace of ABC and computing the matrix product of A and B are essentially the same thing. Except not in some important but subtle sense that Josh is about to.
No, actually, I just realized, just to connect the diagrammatic notation to what we saw yesterday, this little diagram, this ABCD that you're standing right in front of, is the same notation that Graham was using for quantum computing, just rotated 90 degrees. So
oh, yes.
If you're comfortable with qubits going through the quantum circuit here, it's the same thing, just going through. Yeah.
Good, yes. Yeah. I mean, okay, this whole thing about diagrams is also kind of physics inspired because, if you look at Feynman diagrams, there are these things like, here are, let's see if I'm going to get this right. Here's an electron and a positron, and they annihilate and make a photon, and then it turns again into a pair of an electron and a positron. And if you rotate this 90 degrees, here is an electron, wait. But it's turning into a, oh, right, sorry, yes. A positron is just an electron going backwards in time. So when I rotate it 90 degrees, these could both be electrons, these could both be positrons, and then this photon could be a little bit of electromagnetic force which travels from this particle to that particle and causes them to interact. So in quantum field theory, like the total probability of this diagram or the amplitude of this diagram would be the same, even though they sound like two different events. All right, anyway, if I keep making philosophical comments like that, I shall use the hour up very efficiently. All right, so, and by the way, a matrix going backwards in time is its transpose, or its Hermitian conjugate if it's complex. Okay. All right, now, what is this computer science question that a lot of us are interested in? We would like to write this tensor as a sum of R terms, each of which is a tensor product of three n by n matrices. And if we can do this, we say that this tensor has rank R or less. And so, as Josh told us, it's an interesting fact due to Strassen that for 2 by 2 matrix multiplication, we can do this with only 7 instead of 8 terms. And then you use that as the foundation for this iterative algorithm that shows that we can multiply n by n matrices by breaking them repeatedly into 2 by 2 blocks of n over 2-dimensional matrices in only n to the log base 8 of 7 instead of n cubed time. And so figuring out the rank of this matrix, especially in the limit where n is large, is identical to figuring out what is the optimum running time for matrix multiplication. So it's a lovely open question. And just to do this with the indices written out, you can see that this might be tricky. Because I want that to be somehow forced to equal that, and that to somehow be forced to equal that. And certainly that's not true if I only had one term here. So somehow with more terms I have to make this happen. And for example, if I take this little diagram, which forces I to be equal to j prime and j equal to I prime, and so I was asking how many terms do I need to make that diagram? Well, that's just a matter of its matrix rank. But its matrix rank is, the rank of this n squared dimensional matrix is n squared, right? It's full rank. So here we know exactly how many terms we need to do, but with this tensor we don't. All right. Okay. So now you know what the matrix multiplication tensor really is. Okay, so when Josh was a postdoc in Santa Fe, which were some of the best years of my life, I don't know about his, we thought, well, let's just try to find these things numerically. So let's try to minimize, let's say this is approximately equal to this, and let's call this t twiddle. So the goal now is let's choose a target rank, and then as a function of these three matrices, let's try to minimize the L2 distance between t and t twiddle, just the sum of the squares of the differences in all their entries. And of course, if we get this down to 0, or maybe 10 to the minus 30th on our computer, then we'll think that we have found a good decomposition. And we, as I think Josh already mentioned, we were far from the first to do this, and this has been going on for decades with various people trying this. And like our target was for 3 by 3 matrix multiplication, can we get R below 23, which is the best known upper bound. And I don't know if you've talked about border rank at all. Okay. Yeah, there's a more mysterious thing where we don't literally have an equality here, but where we have a family of these things where as some entries go to infinity and others go to 0, we get closer and closer to the tensor we want. And if you can do that and really have the L2 norm tending to 0, then we would say its border rank is at most R. But those subtleties of algebraic geometry we can perhaps leave on the table for now, especially because I don't fully understand them. Okay, so again, I want to minimize this as a function of u, v, and w. So let's write this out. This can be written as, this is the total norm of t. Quick, what is the, if you will, let's see, should I call it the Frobenius norm? What's the L2 norm of that tensor? Well, let's see. This is the inner product of t with itself, and that's the trace of t times its transpose. And that means I take this diagram and put it on top of its transpose, which is its, mirror image, and then loop everything around. And you can see I have 3 loops here, and each one corresponds to an index which can range from 1 to n. So this is n cubed. By the way, what's the trace? Ah, well, the trace is just this thing like that, and you can follow it around and see there's just one big loop. The trace is n. Isn't this fun? Okay, all right. Okay, so it's the trace of t, which is n cubed, and, sorry, it's the L2 norm squared of t, which is n cubed, and then I have this, and then I have minus their inner product. And so I already said that's n cubed. What is this? This is what I get if I multiply this thing by its transpose and take the trace. And I will get some cross terms here. So this is, I just realized there's a notational problem. You want me to move myself or the writing?
The writing. Just like, yeah. That's
or can we just move the board?
That would be nice, but yeah. No, if you just start that cell like a foot to the right. Yeah.
Okay. All right. By the way, there was a notational problem here. Each of these, and this is kind of annoying, has a subscript s saying which of these matrices it is. Good. So this is the sum over S and T. Is that far enough over?
Other way.
I asked you to be gentle with me today. And how's that?
That's excellent.
Okay. Okay. So I have the inner product of these things with themselves, but I have these cross terms, so like US, UT, VS, VT, and WS, WT. And then this, well, this is nice because what is the inner product of T with something? Well, it's the trace of T times the transpose of that thing, but what T does is produce matrix products, right? So this term is minus 2 times the sum over S of the trace of the matrix product of these three things. Okay, so that's kind of cute, because that's what T does. That's its job. Okay, so now suppose we want to try to minimize this in the clunkiest possible way. We're going to do that by, this board doesn't move up, does it? It's not that kind. Okay, so what should I keep and what should I erase? I'm going to erase this stuff. Okay. Good. So I'm going to take the partial derivative of this with respect to the entries of one of these matrices, say WS. And what I mean by this is the matrix of partial derivatives with respect to the different entries of WS. Okay? Because I'm trying to minimize this. And what do I get? I'm going to put a 1/2 out here because that will cancel this too, and also WS appears here twice, once because of when S is S and the other when T is S. And so I will get the sum over T of these inner products but the derivative of this with respect to WS is just WT, okay, because it's an inner product of the two. And then from this term, well, by the same argument, this is the inner product of US VS transpose with WS. And so the derivative of this is just that. And let's say I'm trying to set this equal to 0 to minimize this function. Well, now I have a bunch of equations. And by the way, what am I doing? I mean, this whole function is a bit nasty as a polynomial in the entries of these matrices, right? It's a 6th order polynomial. But luckily, if I focus on any one of these matrices, it's only quadratic. Okay. So that suggests an iterative algorithm where we repeatedly hold two of these fixed and vary the other one to minimize it. That's what we're doing. There is no guarantee that this algorithm will reach the global minimum, but it will presumably reach some local minimum. See you with me? Okay. And indeed it is called iterative least squares or alternating least squares. And I think lots of people have written it down, and including like one kind of major player in this field is Tammy Kolda, and there are lots of other people who've talked about this kind of thing. Online, if you're looking for this, there's some communities call this the canonical tensor factorization, and there are various portmanteaus that have been written down, like Candicomp and Parafac, and there are large Wikipedia pages on kind of fancier versions of what I'm telling you. Okay. Anyway, just to finish this up, let me take all this, these are just numbers, they're just scalars for each S and T, so I can call this an R by R matrix MST, and then setting this equal to 0 gives me a nice update equation, which is that I should set WS equal to the sum over T of the inverse of this matrix times times this, but for, right, T. Okay. Now, this is not necessarily the best way to really do this numerically because this matrix might not be it might be almost singular, and so then we would just ask some software package to solve this as an iterative least squares problem instead of explicitly multiplying by the matrix inverse. Okay, so like I said, this is very classical, and we tried this for 3 by 3 matrix multiplication and didn't really get any new results. So there were already rank 23 decompositions known that go back to, as he said, Lederman, although it's really annoying, actually. If you actually look at Lederman's paper, it's sort of infuriating, because basically one page gives the 23 terms, and another page says, oh, well, I took all these polynomial equations and I found a nice way to divide them up, and a lot of them are cubics, and I solved those, and, you know, then I found this solution. And some other papers are also annoying because they say that they did this, and then after they got the error to be 10 to the minus 30th, they then took all the resulting matrices, which of course were big, you know, were dense matrices full of real numbers, and they said, then we straightened them. We found nice bases in which all their entries were +1, -1, or 0. So how did you do that? They didn't tell us. Anyway, when you do this in practice, you find that the landscape of this optimization problem is very bumpy. So you get stuck in lots and lots of local minima of this L2 norm. And that's kind of interesting, that there are lots of local minima, because the fact that they are local minima, there has some interesting algebraic flavors here. And I'm going to give you a conjecture based on our numerical experience. Here's our conjecture. If the minimum of the L2 distance, in other words, if there exists a t-twiddle for a given r, such that this is anything less than 1, okay, then, in fact, I'm going to say lim inf because we might have one of these funny situations where we get closer and closer as these entries go out to infinity, which can happen with tensors. Then the lim inf of this is 0, and therefore the tensor rank of matrix multiplication, or maybe the border rank, whatever you call that, is less than or equal to whatever r you had here. In other words, what am I saying? That when you do this numerical minimization or any other form of numerical minimization, anytime you get this distance below 1, it actually means that there is an exact decomposition, or it's okay that I'm telling them this, right?
It's a little late now.
We were really excited. It's a little late now, yeah. Anyway, or there's a sequence, okay. That would be great, because if this were true, then you would actually have a computer-assisted proof that of an upper bound on the rank. Okay, anytime you get this below 1. Why do we believe this conjecture? Because in every case we got stuck at 1 or went to 0. Okay, that's the only reason we believe this conjecture. We got stuck, for a while we believed the stronger conjecture, that all local minima, in fact, had an integer L2 distance. Why did we believe that? Because sometimes we got stuck at 2 or 3 or 4. Henry Cohn then found a counterexample where, to very high precision, he found a local minimum with like 2 by 2 matrix multiplication and a kind of unrealistically low rank, like rank 3, where the distance was not an integer. But it seems that for some reason, integer distances here are very common. And we still believe this conjecture. So you should try to prove that. If you're feeling kind, maybe include us. But yeah, I like that conjecture very much. There are various sufficient conditions which would imply this. Look at the formula here. Well, this is already an integer. And notice that if we have a local minimum, then actually this equals that. I mean, just undo the taking the derivative of W here that I took, in which case at any local minimum, actually the distance is just this, and this, remember, is just the sum of these traces. So for instance, if it were the case in any local minimum that this times this had integer eigenvalues, then it would have an integer trace. And then the distance would be an integer. This is true, interestingly enough, of most, but not quite all, of the known decompositions for 3x3 matrix multiplication. Okay. So all this is joint with Josh. Now, great. Well, maybe matrix multiplication isn't the only tensor you care about. Maybe a friend of yours has observed a tensor, or as Josh called it, a set of numbers in a box. And maybe you believe that this tensor has some underlying structure, that in some sense there's a ground truth which is exactly rank R, but the real world is noisy, so you think in that case that this is literally a wiggly equals sign instead of an equals sign. And so your hypothesis is that your observed tensor is a low-rank tensor plus some noise. Okay? And now, how would you find what is then the best low-rank tensor to approximate an observed tensor? Well, you might say, well, Chris, you just said that in the special case of matrix multiplication, we should minimize the L2 distance. And in the case of matrices, right, I have some observed matrix. I believe that it is a low-rank matrix, namely I'll sum over something like this from 1 to R, and I believe that it's actually U sub Si times V sub Sj, that's what Mij is. This is a rank R matrix, but then I've added some noise, Wij. Well, if this noise is Gaussian, okay, so let's say that I believe that these entries are independently distributed, and here, let me write it like this, if you don't mind. For instance, what does this mean? It means I think these are all Gaussian with mean 0 and variance 1. Okay. In that case, you all know what I'm saying, right? You know what I'm about to say? Then the probability of that I would, let's see, if you, I'm not really being Bayesian here because I'm not going to do very much today with a prior, okay? So the maximum likelihood estimator would be the one which maximizes the probability of getting M given a set of U's and V's, or if you wish, given a low-rank matrix M, but M twiddle. If the noise is Gaussian and independent, well, this is just the product over Ij of the Gaussian distribution, which up to a constant is e to the minus a half times Wij. But what is Wij? It's the difference between Mij and M twiddle Ij, but then squared. Okay? Right? That's the Gaussian distribution. And so, well, the product of a bunch of exponentials is the exponential of the sum, and then maximizing this probability means minimizing the L2 distance. Okay, I'm saying this in such a long-winded way because we often minimize the L2 distance between things. We do that when we do linear regression, say, most of the time. But in some sense, when we do that, we're assuming that the noise is Gaussian and independent and has equal variance everywhere. Okay? That's not the only good reason to do it, but I would say that at some level, that's what you're assuming. Now, for matrices, of course, we know how to do this. The best low-rank matrix the one, in this sense, the one that minimizes the L2 distance, we can get from the singular value decomposition. And if you haven't derived that in the past year, take a napkin over your beer this afternoon and just do kind of the same thing we did before, and you'll find that, oh, actually, these U's and V's should be the left and right singular vectors. And then you'll feel, oh, this is great. It's like when I took linear algebra 15 years ago, and you'll feel, solid about your knowledge. Good. So there are sort of two interesting things here. One is that for tensors, we don't have a theory of singular vectors and singular values. So we can't just say, take the top R of them. Instead, we're forced to do this kind of iterative thing. It's no longer a convex problem. There can be local optima, and life is more difficult. But the other thing I want to say is that if we have a different notion of noise, then minimizing the L2 distance is simply not the right procedure. Okay? And that's what I want to talk about in the remainder of today. No one has asked me any questions so far. Most of you seem to be paying attention.
What I'm sort of confused by is that your goal that you're going to start by sampling random tensors with this probability, or is it that you've already had some other sampling in mind and you're trying to analyze it?
So as a moderate Bayesian, the question was that am I implicitly sampling? Am I sampling these random matrices or random tensors? Right. Okay. So good. I'm imagining that what nature has done in the process of producing this data is taken some ground truth low rank matrix or tensor and added noise to it. And that the data that my friend in, say, the social or life sciences has observed was produced by that type of process, and that it is now my job to try to reverse that process to the extent we can and recover, at least approximately, what that true matrix was that nature started with before adding noise. By minimizing this, I'm doing what people call, in this acronym-ridden field, the maximum likelihood estimator. Of course, if I am really wearing a Bayesian hat, I'm not interested just in the M-twiddle that maximizes this probability. I want some sense of the posterior distribution because I want some sense of, well, how certain am I of that estimate? And that might depend on what the variance I think is. Here I, for simplicity, set it to 1. And, I know that Bayesians and frequencists are kind of like Catholics and Protestants a few hundred years ago, but I think I'm a moderate Bayesian. So I think that the Bayesian framework is a reasonably good way, although not the only way, to model our uncertainty given the data.
Do you allow me to drill down a little bit to understand the model better?
Please, and I'm obligated to repeat all the drilling.
I'll do my best. So,
He said drilling, that's why I made that joke. For those of you at home.
A table, your scientist is doing a bunch of measurements and filling this grid.
Yes.
Is it your model that every entry is affected by independent events, or that along the entire axis there was some air that was being propagated through the table?
The current model is that each entry was an independent Gaussian, and that could have come from randomness in nature itself before my friend attempted to measure it, or it could have come in error in the measurement process, or both.
So error in the measurement process, I would think of as sort of being like everything that was in the x direction was off because my ruler wasn't so precise. That's different than saying independent in every coordinate.
You're right. I guess what I would say is, hey, look, first of all, I assumed additive noise here, which I'm about to move away from. Okay, sorry, the questioner just asked. Wouldn't you imagine, for instance, some kind of systematic error in a particular direction? Absolutely, you could. That would mean that this noise matrix would be drawn from some joint probability distribution, whatever you want. But If it's a complicated probability distribution with a lot of correlations, then maximizing the probability might get a little bit harder than what we did here. And indeed, I think it's fair to say that in this business, there's this sort of, there's kind of a tension. We assume noise models, or in Bayesian terms, priors, that we may or may not actually believe, but which are mathematically tractable and which we think are not wildly unrealistic. And, so, yeah, anyway. Good. Some of my best friends deal with real world data, so, yeah. Okay, anyway, so let me show you a different model. And this will probably take up the last 15 minutes. So this was the observed matrix is a low-rank matrix plus independent Gaussian noise. Suppose that your observed matrix is a bunch of non-negative integers, most of which are pretty small. It might be the number of times something happened. It could be the number of times a given word appeared in a given document, or the number of times someone called someone else on the phone, or something like that. In that setting, Gaussian noise seems pretty crazy. I mean, I guess if the integers are so large that they might as well be real numbers, maybe. But if they're small integers, it seems like an odd type of noise to contemplate. Let's look at a different one where our observed matrix, Mij, each entry is going to be Poisson distributed. And the mean of that Poisson distribution, that is going to be the low rank matrix. And let's see, I might kind of keep writing twiddles. I guess I could write twiddles. I don't want to write any more twiddles. I'm going to call this mu for mean to distinguish it from m for measured. Okay. And so, again, I'm going to assume that mu ij is this. That mu ij is a rank R matrix. And let me remind you that the probability that a random variable x, the probability distribution for the Poisson distribution with mean mu is this. Okay, so Poisson with mean mu. So now let's again assume that I want to maximize the probability of getting this m. So I'm again trying to do the maximum likelihood estimator, which is not, I'm not saying that's necessarily the thing to do, but let's say that that's the thing we're trying to do. Well, let's write this out a little bit. So the probability of m, these are independent events. So it's going to be the product of all of these. And yes, I will write this out. Oops. Okay. But let's take the log of this. So now we're going to maximize the log likelihood, as we say in this business. And now I'm going to write out what mu ij is inside this logarithm. And by the way, I want to maximize this as a function of the u's and v's, but this capital M here is not a function of them, so it just alters the log by a constant, so I'm going to ignore it. Okay. I want to maximize this as a function of the u's and v's. And I know I'm just dealing with matrices here, but in this case, the extension to tensors is pretty straightforward. So looking at this for matrices is interesting. And by this way, this problem has a name. It is called Poisson matrix factorization, or, if you wish, tensor factorization. And I mentioned that one of the ways that this integer data could arise is the number of times we could have a matrix where Mij is the number of times in which that document I contains word J. And in fact, what I'm describing to you is very close and, or in some cases, is identical to some of the simpler sorts of topic modeling. If you've heard of topic modeling, things like, well, LDA, which stands for latent Dirichlet allocation, is a fancier version of this that has a prior. This is more like its predecessor called PLSA, which I wish I didn't know what all these things stood for, probabilistic latent semantic analysis. I don't know what else I could be doing with the neurons that are being wasted on remembering these acronyms, but anyway. Okay, good. Now, let me tell you something cool, actually, about this sort of thing. And this maybe is only distantly related to tensors, but I think it's wonderful. A log of a sum is kind of an annoying function. And I could just take derivatives of this, but then I would have the sum in the denominator, and it would be kind of horrible. So I want to show you something beautiful that you can do instead, which is called a variational trick. And I promised in my abstract that this is going to have something to do with statistical physics. And it kind of does. And tomorrow we'll have a bit more. So suppose I have the log of a sum of something, which I'll call x sub what I'm summing over. Okay? I'm going to do a couple of things which will look like trivial algebraic manipulations, but it's actually very cool. Let Q sub s be any probability distribution over S. Okay? In that case, well, this is obviously equal to the sum over S of Q sub S times X sub S over Q sub S. That would be true whether Q is a set of probabilities or not. But this now is the average of X over Q if S is drawn according to. So if you don't mind I don't know what notation you like. I have grown to like this bold E for expectation. So if S is drawn according to Q, this is the average of X over Q. But Jensen's inequality tells us that we don't have to name it after someone if you don't want. The log of the average is always greater than or equal to the average of the log, because the log is a concave function. So a lower bound on this is the expectation of the log. But let's write that back out again as a sum. I said a sum. Q sub s log x sub s, and then I could write the log of 1 over q as a separate term, q sub s log q sub s. Okay. Well, this is the entropy of this distribution, the Shannon entropy. You know the story of when Shannon was writing his monumental paper on communication theory. He asked von Neumann, hey, I have this quantity. It's the sum of the probability times the log of the probability with a minus sign in front. And von Neumann said, oh yes, we physicists call that the entropy. So anyway, now this is a lower bound, and it holds for any distribution Q. And remember, notice this, we're going to try to maximize this thing here. So for any distribution Q, you can get a lower bound. So one game you can play in more complicated inference problems is say, well, I can't figure out the real distribution in some sense, but if I make a decent guess, then I'll get a lower bound which is fairly close to the truth. And that's often a good idea. In this case, we don't really need to guess. Let me just point out, exercise to do over lunch, this holds with equality if Q sub s equals X sub s divided by this whole sum. In other words, the right distribution to put here is the actual fraction of this sum consisting of X sub s. Okay? In my 5 remaining minutes, well, really? Okay. Cool. In physics, this thing is e to the minus 1 over the temperature times the energy of some state in our set of possible states. This is called the Boltzmann factor. And it's because Boltzmann taught us that in thermal equilibrium at a given temperature, the probability of being in a given state, it's higher for lower energy states because rocks do like to fall down, but when things are worn, they're sometimes in higher energy states, and that the probability is proportional to this exponential. Okay? At very low temperature, we really care about the energy, and we're almost always in very low energy states. At very high temperature, this exponential becomes quite shallow, which means you're more willing to be in any state willy-nilly. When you work this out, this we call the partition function, this we call the free energy. I'm not going to go through this, but if you remember taking a thermodynamics class a long time ago, this equation is the same as the equation that the free energy is the average internal energy, which is the average of the log of this thing. You see the log will have the energy in it, minus there's a factor of temperature, and then the entropy. Yes?
Just notation, the whole left-hand side log of the sum of xs is what is equivalent to Boltzmann constant, or just something inside that whole thing?
This whole thing, so if you really want to connect with the, if I call this, sorry, let me call this z, this sum is z for the partition function, then the free energy in physics is minus the temperature times log z, which is why there's a temperature that popped up over here. The minus sign is, I mean, I don't want to belabor this, but do you want me to go?
The negative es is pointing just to the xs for the whole left-hand side.
Sorry, this is just this term. So this refers, S is a particular state the system could be in. E sub s is the energy of that particular state. And this correct distribution here, in that case, is this Boltzmann factor for that one state, but we have to normalize the distribution. So we divide by this entire sum. And this is the Boltzmann distribution or the Gibbs distribution. And when people in machine learning talk about Gibbs sampling, they mean sampling from this distribution. Okay. Anyway, okay. So I think it's lovely that some of these things that are really just information theoretic or about this variational maximization are identical to things in a lot of classical thermodynamics. Now, so what have I told you? If you want to maximize this, well, one of the things you can do is maximize over Q sub s, because any Q sub s gives you a lower bound, and moreover, I've told you that for this choice of Q sub s, this lower bound is tight. It holds with equality. So what that tells you is that the maximum over all distributions of this is equal to this. Okay. What that means is that the maximum of this quantity over the u's and v's equals the maximum of a slightly more complicated quantity over u's, v's, and a bunch of distributions q. And we would still have this thing here. but now I would change this log of a sum to a sum of a log. I have a different distribution here for each I and j, because I actually have a different sum inside here for each I and j, qijs, and then I have log of usi vsj over q sub ijs. This sum of logs is easier to take derivatives of. And so here, I'll fit it right in here. So when we set the derivative of this with respect to the u's, the v's, and the q's, we set those derivatives equal to 0, we get some nice little update equations. It's again an iterative algorithm, like the least squares algorithm I showed you was for tensors. Here it's an iterative algorithm even for matrices. Okay, so again, we can't just jump to the SVD in this setting. So I will not actually take those derivatives for you because I'm out of time, but we get things like this. UISI equals the sum over j of our data, Mij, times Qijs over this. You notice there's a symmetry here between u and v. So there's a converse equation where we have v's instead of u's and we sum over I instead of j. And then our update equation for the q's is this one, that the correct value of the q's are our current estimates of u and v divided by the sum of those current estimates. All right. Now, I don't want to just fill the board with chalk. I have a hard time doing math that I can't interpret at each step. So let me just point out, suppose we're talking about topics. Okay, I have a bunch of documents, they're articles about, they're news articles. We think some are mostly about sports, some are mostly about science, a few are a bit about both the science of sports or the sport of science or something. Then we would say that, so S here, we have let's say we have R different documents, okay, because you have 100,000 documents, your goal is to explain them in terms of, say, only 3 different topics, science, sports, and politics, the royal family. Okay. And so US sub I is, for instance, the relevance of document I to topic S, like roughly the number of words in that document you would expect to be directly related to topic S. VSJ would be the relevance of word J to that topic. And then the average number of times that word J would appear in document I would be this kind of sum. That word might be relevant to multiple topics. And so we would get a total number of occurrences, which would be this sum. Okay? So how do we estimate this? Well, we look at the total number of occurrences of J in document I, but weighted by our current guess of the probability that when it does occur, it's because of topic S. That's what Qijs is. And this is just a normalization. So you do this iteratively, and again, like iterative least squares, you'll often reach a local optimum. Thank you very much for coming. You often reach a local optimum. In practice, you might have to run it many times. And if you do all this for tensors, it's not that much more complicated. There's just another sum on the top and another sum on the bottom. Okay, so these are some ways to find, the exact tensor rank is very hard. Not only is it NP hard, but for matrix multiplication, it's like, we really care about it, and that one example is hard. But these are some interesting procedures to find low-rank approximations to tensors, which are in fact popular out there in the real world where people deal with real boxes of numbers. So I wanted to show you those. Tomorrow, I may or may not show you any actual slides from an actual paper I wrote with an actual anthropologist and an actual applied mathematician and a statistical physicist about some anthropological data from field work in Indian villages where we did something very similar to this to try to understand. There, the layers of our tensor were who is friends with who borrows money from whom, who watches who asks whom to watch their kids, who would you ask for a job, who would you ask for advice. So each of these is like an adjacency matrix, and all these layers made a tensor, and we wanted to know, for instance, how these different social relationships were related to each other, and so we used this kind of thing. Okay. Whether or not I show you that, I want to show you some more theoretical stuff about something called the planted spin glass, and I'll just explain that tomorrow because I'm out of time, but you'll like it. Okay. This is great. We didn't have to use the projector at all. Yeah?
Can you come at this over a finite field and just think of replacing reroute Shannon complexity with, do a Hamming distance or something instead and think of it more as an error correction?
I mean, you can write that down as an optimization problem.
Right.
With discrete values, I'm not sure what we would do. Would we take derivatives, or would we do some kind of Hensel lifting-y derivative thingy? I don't know. I mean, so you could certainly write it down. I just don't know how you would solve it. But here as well, I should emphasize that there are really no theoretical guarantees about how well this will do. I mean, in practice, it seems to work pretty well if the data is actually generated by roughly the right, the number of topics or whatever that you guessed. People use it a lot in practice, but I don't know of any non-trivial guarantees even that you'll reach the global optimum, or I should say that you won't be too far from it, because it's a high-dimensional space. I mean, typically the dimensions of this matrix will be quite large. So I'm not sure that, his question was, what if we did this over a finite field, and then maybe the thing we would try to minimize would be the Hamming distance, or you could have, you could have additive noise over the field. There's a problem called learning with errors, where you take a bunch of linear equations over a finite field, and then you perturb the right-hand sides of these linear equations with, if I recall correctly, if you're working mod p, where p is fairly large, maybe I'll add or subtract p over 3 or p over 10 or something mod p. Does anyone here know? You look like you know something about that.
Well, I know you might use small errors. You might have work with large p, might be in a large dimension. You might add.
Okay, all right. But I guess that problem is thought to be so hard that it is currently one of the proposed the foundation of one of the proposed post-quantum cryptosystems. In other words, classical cryptosystems that, unlike RSA, might remain secure even if people can build quantum computers. So I think once you move to finite fields, at least depending on the model of noise, it could be very hard. I mean, of course, the other thing I'm doing here is I've really moved away from the type of framework of computational complexity that Josh was describing, because there, when we talk about a problem as NP complete or something, we're always saying in the worst case. So an adversary has cleverly constructed an example of that problem which encodes some other complicated problem, and therefore we can't solve it without solving that one. Here, I mean, I'm explicitly assuming that nature isn't trying to fool us, right? I'm assuming that there is some ground truth, and that then there's some well-defined probabilistic process which has been fairly applied to produce our input. If you read Norbert Wiener's Cybernetics, he has a lovely passage on the Manichaean versus Aristotelian devil, the adversary, So the Manichaean one is trying to deceive us. So the Manichaean one is really trying to create problems which break our algorithms and are tricky for us to solve. If I recall correctly, the Aristotelian devil is merely, well, life is hard, there's a lot of randomness, there's a lot of uncertainty, we're fumbling through the fog, but nobody is trying to deliberately mislead us. Computer scientists live in a cold-hearted world, a very pessimistic world with the first type of devil, for historical and cultural reasons. Maybe also it has to do with their personalities, I'm not sure. And this is more the second kind. Yeah, so cryptography, of course, lives largely, I mean, in cryptography there really is another devil, the worst possible kind, a human being who is, really trying to confuse you and break your codes and not let you break their codes. And so, yeah. So maybe it's because computer science came of age in World War II. Any other questions, or shall we have lunch? Okay, thank you.